Dale, thank you, and thank you, Don, too. Thanks for the introduction, and thanks for inviting us here. Really appreciate the chance to get up and speak to your users about this. And I'd also like to say that in my many, many years of going to conferences, that hands down, the swag that we got from this conference is the best I have ever gotten. Does everybody agree with that? It's the best, okay? So thank you. So I'm going to talk to you today a little bit different. I'm, as Dale said, from Erdos many years ago, started there 32 years, and I've been doing Raster for many, many years. Something Dale tells me they said they were never going to do it safe, but I believe they're doing Raster too. So we find many things come together in what we do. And like he said, I'm part of Hexagon Geospatial, which has just formed at the beginning of this year, and so that's change. And what I'd like to talk to you today about is change. Change is the one thing that we can count on every day. And change results in a lot of data. There's a lot of kinds of change that we have in the world. This, for example, is an area of mining. And mines, all they do is change, right? They dig, they change the landscape. You can have change coming from natural disasters. Here's this tremendous flooding. Notice these people cut off totally on this little bridge over a road. Or in forests and silviculture, you can have change because of infestation, because of disease. Here's just another form of natural change, just effluent, growing land at the outlet of a bay. Or just changes in natural habitat and wildlife. Or just the wind. The wind and the weather are constant efforts of change. And here's an example I'd like to talk about just a minute. This happened on the West Coast back in 2006. Some of you may be familiar with it. This area was on the coast. Looked like this one day. The next day it looked like this. The land just dropped away. And when something like this happens, what do? We need to find out about it. We need to get information. And one of the ways that we can get information is through remote sensing and through a variety of sensors that can be deployed. In this case, an example is a drone, which I'll talk a little bit more about. But there's a tremendous amount of data that can now be gathered when something happens. And what do we do with that data? Well, we have to collect it. We have to store it. We have to manage it. And we have to analyze it. And we do all this so that we can respond accordingly, so we can come up with the right information to take the right actions. And this is really what Hexagon has been focusing on. Hexagon, many of you may not have heard of. Hexagon has been focusing on acquiring companies and technologies in sort of the measurement arena. You might know Leica Geosystems, they're part of the Hexagon family. Intergraph is part of the Hexagon family. Many of these companies in the geospatial industry are now part of the Hexagon family. And it's because Hexagon wants to have this notion of fusing the real and digital world. They want to be able to take information from the sensors, from the acquisition, through the software that analyzes it and builds a digital model. And it's not a static process, of course, because there is always change. And so this cycle of collecting information, updating your model, is a continuous one. And so what drives this engine of change or of analysis is the data that goes into it. And there's a growing number of sensors to collect this data today. So you've got certainly things like these GPS sensors. You can go out and collect 1 centimeter accuracy, a point at a time, sort of what a surveyor might use. But perhaps more traditionally, you've got these things that are total stations. Total stations combining GPS and laser ranging. I can go out and measure a point. And the newest versions of these things, called multi-stations, allow me to measure not just 1 point at a time or a few points at a time, but tens, even thousands of points at a time. So I can go out and measure volumes with these devices. But at the same time, I've got these things which are called high-definition scanners. Now, these are terrestrial lasers. And these terrestrial laser scanners allow me to do things like measure the as-built infrastructure of a factory. And I can collect billions of points with these things. I could take these same sorts of things and put them on an airplane called a LiDAR, right? Airborne laser ranging or LiDAR systems that can collect billions of points at a time. You've got now the capability of taking that not just on the surface, but down below the surface of water for nearshore bathymetry with laser ranging. There's also optical. Sort of traditional optical cameras, small format digital optical cameras can be used not only for nadir type imaging, but also for oblique imaging, so that I can build a lot of these models and populate a lot of these models you've seen, to more traditional large format digital cameras, and even things like this push broom digital aerial camera that allows me to sense things at about 12,000 pixels per row in 7 bands, but I can do it for very long continuous swaths that give me stereo pairs along the entire collection. To that, you can add things like satellite imagery. There's a number of satellite companies, traditional companies, but there are some upstarts coming with some very interesting new ways of collecting and imaging that I'll talk about. And then, even more recently, there are the UAVs or drones. We've heard about the drones a lot in military actions, but they're coming into commercial use. And so there are a variety of these, as well as automobile-borne or vehicle-borne sensors that can now collect. And this is all resulting in an increasing variety and quantity of data. So, of course, vector data is not something that we collect from sensors, but you saw yesterday OpenStreetMaps. You could almost treat the entire population as a sensor, if you will, for the traditional vector data. But to that, you've got aerial imagery, you've got satellite imagery, which sort of is the area we come from. Starting with the Landsat program, you had multispectral data for doing things like land cover analysis, land use analysis, to hyperspectral data, which hasn't caught on to a large extent because one of the first commercial hyperspectral sensors went into space, also went into the ocean, so it was never very successful. But there are still hyperspectral sensors around, and they're, in my opinion, experiencing a comeback now. Radar sensors are being flown. I'll talk a little bit about radar and why it's important and why it's useful. Thermal sensors, also a different kind of optical sensor. And now you heard a little bit about point clouds. Point clouds are huge. Point cloud sensors have a tremendous number of benefits, and they are being used throughout the industry to do things like provide elevation data, which used to come from more surveying techniques. But that's all just data. Before it can become information, it has to be processed. It has to be analyzed in some fashion. Some of the sort of processing you can do is just sort of visualization. If you have good tools to take the data and look at it, you can use the human as the analytic piece, and he can analyze it that way. Of course, you need to even enhance the data before you look at it, or to help you see what's in the data. You can still do analysis like measurements. Heads-up digitizing is a way of extracting information from it. But then there's more sophisticated techniques like automated classification for land use or segmentation for feature identification. And once you do that, what have you got? You've got sort of GIS data coming out of the imagery, but you can then further take that and do other GIS-type analytics on this data. The end result oftentimes is a map that goes back into a system like perhaps you saw Robert show today. But to do all of this, you need a rich set of tools that let you do all of these things. You need tools that have simple, intuitive GUIs that are easy to use, compelling. But you also need, behind the scenes, powerful and dynamic spatial modeling. I need to be able to take information from each of these kinds of sensors, extract information from them, and put it together in novel ways. And this includes the technologies from a variety of domains, from GIS, from remote sensing, photogrammetry, and even serving technologies. And today, because of the increase in clouds, the increase in computing capabilities, you need software that can run in a distributed mode, that can take advantage of the CPU power that you have. So who uses all of this type of data? Well, probably everybody in this room uses this type of data, whether you're a local government doing, say, street mapping for your county or your state, whether you're a defense agency who needs to do monitoring of activity in other areas. You're going to use remotely sensed data and these kinds of tools. If you're a utility, I know there's several utilities people in here, and you would use this sort of data to monitor, for example, encroachment of vegetation on power lines. Or if you're in the exploration business. In your exploration business, they also use remotely sensed data coupled with other kinds of information that's gathered to find out information about likely places to drill or likely places to dig, as well as people who have to manage natural resources. As a matter of fact, this was the emphasis for the Landsat program many years ago, was natural resource monitoring. So let me talk a little bit about point clouds. Point clouds are in use everywhere today. You saw point clouds used in the Autodesk presentation. So they come from many places, and I'm not calling it LiDAR, I'm calling it point clouds, and you'll see that very commonly. We already mentioned that you can get point clouds from these variety of terrestrial sensors as well as these airborne sensors that let me take digital surface models as well as near-shore bathymetric models. But point clouds can also come from optical imagery. So there's now a new technology called semi-global matching that allows me to take two stereo pairs of imagery, or a stereo pair of imagery, and extract LiDAR-like point clouds from it with very high accuracy to within about a pixel of the original collect. And so what can I do with point clouds? Well, I can do a lot of things with point clouds that I could do with imagery. As a matter of fact, point clouds are kind of like an image, especially when they come from SGM, because they've been collected at sort of the same resolution, almost the same spacing as you would pixels from the imagery. So you can do typical 2D visualization techniques like this color-based mapping, intensity-based mapping, class-based mapping. But the nice thing about point clouds is that they're 3D. They're not just 2D. So now I can look at them from the top, but also from the front and from the side. Well, when I do that, I can see a lot more information than I can just looking down, and I can start to take measurements. And this is real information. This is what was out in the field. So like I mentioned, you can do vegetation encroachment assessment with it. So a person whose job it is to make sure that the vegetation doesn't grow higher than a certain amount, he doesn't have to send field crews out all the time now. If he has a good LiDAR collect or a good SGM collect from the area, he can use tools like this to do it. And think about that presentation yesterday when the man was talking about the airport and they have these zones they have to monitor. Well, you could use point clouds to help do that in an automated fashion to make sure that nothing encroaches that airspace limit. And here's a little movie, another thing that you can do with point clouds. Another thing that people in mining have to do is they have to keep track of what is where and what sort of tailings and what sort of piles they've created. So here's an example of a LiDAR data set at this mine. And the person is digitizing these 3 different piles that they want to understand the volume of. So all you've got to do is digitize around the boundary of them. And when that's done, we go up, we pick a tool, and have it give us the exact volume of those piles. So now you don't even have to go out into the field to collect that information. So the points that are created through SGM, I call them LiDAR-like point clouds. So here's an example of data created by an SGM. There's another example doing the same sort of things we saw before with the LiDAR data. And the nice thing that we can do with this is we can now combine point cloud data, not just for visualization, but also for analytics, so they can be fed into a variety of processing to improve results. And because the points are collected from the imagery, they can be colored with the imagery. It's sort of like having an ortho combined with the points. And you get photorealistic results from a point cloud, but you can also do real-world measurements on it. And when you have these dense points like this, you can do automated building extraction. So now you have a scene like this, which is totally automatically extracted from a set of images from which point clouds were extracted. And you could certainly use something like this to populate the kind of models that you were seeing earlier today. So this is not a model in the sense that it was originally digitized. This came from the actual, from imagery, and it's a very real-world model. How many of you have ever looked at radar data? Oh, quite a few, quite a few. Radar is well, it's a technology that's been the up-and-coming thing for quite a while, actually. One of the reasons is it hasn't caught on more is sort of the lack of tools to deal with it. It sort of takes a specialist, but radar is very special. And Canada was one of the companies that sort of pioneered this with the RadarSat program, RadarSat 1 and 2. They were used to do ice mapping in the shipping channels, very important for that. But many other countries are now putting up radar satellites, including Germany, India, Korea, Japan, and the EU. And these satellites are providing a great amount of information. And so why is radar important? Well, one of the things is different about it is it's an active sensor. Most sensors are passive. They are illuminated by the sun. That by itself says that, well, they've got this limitation. They're only good where the sun is. If it's nighttime, they're not good. Radar is self-illuminating. It's got its own source of energy, which means that radar can be used day or night. And the other thing is the radar data, because of its nature, it can penetrate through clouds. So radar is not obstructed by clouds. You have a greater amount of time that you can collect. Radar is also interesting because you can use the interferometric aspect of it. You can measure things based on the wavelength of the radar data and its coherence. And I'll talk a little bit more about that. So this is an optical image, North Sudan. Data came from Urimaj. It's a very sandy area. One of the neat properties of radar is that it can penetrate sand a little bit. So while you don't see a lot of detail here, when you use a radar image, there's a lot of subsurface information that you can see. So radar lets you see things you could not otherwise see. Radar has been sort of, like I said, traditionally difficult to use. People don't understand it. It looks a little different. But we're providing tools that make it much easier to use, much easier to do things like this change detection, sort of this color-based change detection where blue is new and red is old, so that means the blue things have just appeared, the red things are gone from the previous scene. But another thing you can do with radar is detect very small amounts of change. And that change comes from what's called a change in coherence. A very small amount of disturbance can change the phase of the return signal. And it's this measurement of phase that allows you to do very fine change detection. So the image on the left is what's called the magnitude image. That's just what you take if you just take radar data and look at it in a viewer. That's what you see, and you don't see a whole lot. On the right, if you take the phase component, you can see this. What are we seeing? We're seeing tracks in the desert where there was movement, where there was some sort of building going on. And so just the vehicle's tracks that they left in the sand displaced it enough such that it caused a change in the coherence, and that could be sensed using radar data. You could not do that with optical. And because of this ability to detect changes at the order of the wavelength or the phase change of the radar data, it can also be used to do elevation extraction if you have radar pairs. And so radar can be used to give very high resolution elevation data. So on the left is this very high resolution elevation data that came from TerraceRx versus a USGS 30-meter DEM. And that same property can be used to do subsurface, or subsidence. So this is an area of subsidence that has happened because of water being pumped out of an area for irrigation or for some other kind of use. And I keep thinking that this kind of thing might have been able to be used to predict that landslide that we saw in the previous thing, because there had to be slight perturbations in the ground before that. So drones, UAVs have been used by the military for a long time. The proper term is UAS, unmanned aerial system. A UAV is a part of a UAS. But now they are coming into the commercial realm. So you have sort of these long range as on the top and these sort of shorter ranger ones on the bottom. They can now be used for a variety of different applications. And they can also carry a variety of different sensors. Sensors like just typical optical sensors, LiDAR sensors, small LiDARs, but more and more you see video sensors carried on these UAV or UAS devices. They can also be used in applications that aren't just strictly mapping, but in this example, power companies can use these things to monitor the power lines. They cannot have to send humans up on those dangerous lines. Now you could use these devices which can be programmed to fly quite precise paths to go do the inspections that people would have had to do in the past. And you can also take this video type data and map it. So now we've got this video data being mapped onto a map on the left in context so that I can see the things around it. I can see it with my other GIS data if I'd like to. So now video is another one of those kinds of data that I can combine in my stack with other kinds of information in my GIS. So I said we started with Landsat. It was Landsat many years ago, very low resolution, 30-meter data. Quite a few years ago, it went up to 1 meter. Now, from places like Digital Globe, I can get 30 centimeter natural color data from a satellite. It's a tremendous amount of data. So that spatial resolution has been increasing. Well, recently Skybox and another company called EarthCast, they're launching constellations of small satellites, and the approach there is to have very high revisit time. So now they're improving the temporal resolution. That is, I can get more and more data samples in a particular amount of time. So here we are looking at this on a day-by-day basis. I have a new scene, and I can see things change. I can see ships come and go. I can see changes in the water over just a very small span of time. And this one, I really like this one. This is panchromatic. This is video from space from the same company. See the airplane? It caught an airplane going past. You see its shadow come back on the top. And watch, you see cars moving. Imagine the amount of data that this is resulting in. And imagine what you might be able to do with this sort of information. So it's great. We collect all this information, but we've got to do something with it. You've got to extract information from it. And it's very disparate kinds of data. And we want to be able to bring all those things together. And one of the things that we've done recently is create this thing that may seem familiar to FME users, this spatial modeling, this graphical spatial modeling interface that allows us to have a very deep toolbox of capabilities that fuses many different of these genres together, and it's graphical to give you a very intuitive environment. And it's this very environment that we've been talking with Dale about, gee, wouldn't it be a great idea if we could have FME sort of plug into this some kind of way? We don't know how that's going to be yet, but it's a very interesting idea. And so in this environment, you can work with raster data. And one of the things I like about it is you can look at it in real time. So as I make a change to my model on the left, I see the result in real time in my view. But it's not just raster. I can do that with vector data, the same thing. Make a change to the model, see a result. Even with LiDAR data, or point cloud data, I should say. Make a change, see the result. And I can combine all of these things. So here's a model that we put together that fuses point cloud and raster data. As a matter of fact, it's taking the point clouds that come from raster data to do a sort of a unique change detection. It's we make this 5-band image, red, green, blue, near infrared, and Z. That's the elevation because it came from SGM, came from a point cloud. And we can do very clean change detection with this. Some of the best change detection I've seen. So this is El Paso, Texas. The data actually came from an ADS-40 scanner. This semi-global matching was used to extract the Z component, and they do the comparison. And you see down here, we can see these yellow buildings. Those are areas that were demolished from this base at the top. Those green and blue are areas that were built in the subdivision. And those yellow things in the middle on that airport is places where there was destruction or collapse after some kind of storm event. But what you don't see is any false positives, any false changes. It's very clean when you use this Z component. The same kind of thing, the same environment can be used to fuse information from rasters and vectors. In this case, this is sort of a tax assessor-based application where I want to take, I want to see what change has happened confined to the parcel of an area for the purposes, well, for the purpose of assessing taxes. None of us like that, but the parcel assessors like this sort of stuff. And then here's sort of an interesting application of, I said visualization is a part of analytics, and this is just sort of a hotspot mapping application, but it's bringing things together in a way that's different. This is actually using 3D. I take my hotspots, or my crime incidents, I build a hotspot map, lay that on top of it, but then what I want to do is, that's still sort of flat, I'm going to let the hotspot map be a piece of elevation. So now I get a third dimension brought in so that I can interpret this data differently. So it's using a 3D technique to view something that you might not have viewed in 3D before. There we go. And then lastly, what we do is we overlay on that sort of the zones in which this happened. And then you can see what the areas of high crime are and what the zones are in a very unique sort of way. Okay, so there we go. So those are the zones and the event, the numerical occurrence of crime within those areas. A little bit different from remotely sensed data, but a different way to visualize. So I've got all this data. The volumes are growing at an ever-increasing rate. The resolution, the frequency, the coverage are all increasing. The kinds of data that I'm managing are increasing. And the sensors that are providing this data are increasing. And this all leads to a need in an organization for managing this data. I've got all of this data. How do I know what I've got in any particular place? I'm stuck with this bounding box problem. I know I have a lot of information. I have a lot of sensor data, be it optical or radar. I know I've got a location data. I can have data files that are tagged to a place. But how do I find it? And that's what we do with our data management solution called Apollo, is manage this. We allow people to answer this bounding box problem so that you can discover and catalog all of this information, centralize the metadata about it, so that you can then come back in and do queries against that, so that you can find information based on the metadata, and you can do it at sort of very fine-grained queries, looking at many, many different aspects of the metadata. And once you've got all this data managed, I want to be able to process it. And one of the things you can do is take that spatial modeling that you saw, take those models, put them up on the server, and use those in conjunction with your catalog data to provide information, to provide results. And those results need to be provided in a variety of ways. So you've got to have delivery, and this delivery can come in the form of web browsers or mobile devices in either 3D or 2D type presentations. So now all that data that you were collected and making in 3D, I could now look at in my web browser or on my mobile device. So today people might think that disk space is not an issue, right? There's tons of storage. Well, it's probably a bigger issue than ever. So we did a project in Germany. They took the entire country. They mapped it at about 20 centimeter resolution. They mosaicked it together. And it turned out to be a single image that was about 1 terabyte in size. And if you add on the pyramid layers that you need for imagery, that comes out to be about 1.3 terabytes in size. And with typical numerically lossless compression, that gets down to about 400 gigabytes, about a half terabyte. If you use ECW compression, one of the compression technologies that we provide, it gets down to about 50 gigabytes, a tremendously small amount compared to that original collection. Oftentimes people use tiles to do this sort of thing. I want to do tile caching, but with tiles you have the raw imagery, but you have your tile levels, and you have hundreds if not thousands of tiles. They take up a lot of space. With this sort of compression technique, I have the original data plus one small image. And it does make a difference. Here's sort of an example. If you look at Amazon 3 cloud storage, we did sort of an estimate on a per month basis with the original size data as tiles. It might cost you $6,000 a month. With this compressed image, $82. It's real money savings if you use compression like this. And this is just an example of that sort of data. This is that 1.3 terabytes of data being browsed through very seamlessly, can be served over even a low bandwidth connection. And this is the thing that we do have to concern ourselves about with this much data. And now, a very similar thing is being done with point clouds. So point clouds got a similar compression. They can compress the data tremendously, but more importantly, can serve it. So this is data being served to our client through, it's actually coming from an Amazon server and streaming this data in real time. So in summary, I'd like to say our vision and our challenge altogether is to provide the tools that enable people like yourselves to collect, to organize, and to manage the growing deluge of data and effectively make sense of our ever-changing world. Thank you.